Hi, everyone. I'm Michael. I'm a co-founder of Cadabra Systems. Recently, I graduated my PhD from the Technion. Today, I'll talk about a recent work, Arbigraph. Arbigraph is a verifiable execution delegation protocol that is optimized for machine learning workload. It is Turing-Complete and parallel. This is a joint work with Hongyin, Ohad, Gal, and my advisor, Ittay Eyal. So I'll begin with the question, why would we even want to connect machine learning and the blockchains? Our life becomes more and more dependent on online service providers, such as online insurance, social platforms, and online payment systems. The operators of those services use machine learning for automatic decision-making. It can be for content moderation, for claims in case of insurance, acceptance of claims, and even the question of who gets access to those services in the first place. The problem with this is that those decisions are opaque and often controversial. Blockchain is a great way to democratize and decentralize the decision-making for some of those systems. We can imagine a decentralized insurance company that accepts or declines claims automatically using ML. The problem is that currently blockchain is not really great at understanding content, reading documents, judging. It lacks the contextual capabilities that are required for this type of work. LLM are exactly the gap that we need to fill in order to make smart contracts actually smart. But the problem is that machine learning requires millions of operations, and this is, if implemented naively, something that blockchains can't handle in terms of gas and memory requirement, because every node has to replicate the computation in order to validate it. Therefore, we have to use computation delegation in order to include ML on top of blockchains. So before I'll explain our protocol, I would like to give you some background about existing solutions that specifically about optimistic delegation protocols. Usually, you can simplify the setting that we have two parties that are interested in executing a program. The parties use the smart contract as an arbitrator in case of disputes. Usually, the protocol starts when one of the parties submit the result of the computation, and then the other party can either accept it or initiate a dispute process. In case of dispute process, the smart contract acts as a very efficient arbitrator, meaning that the time that the smart contract spends on this should be much shorter than the computation itself, ideally logarithmic in the computation. We identify 4 phases for optimistic protocols: the commit, run, dispute preparation, and dispute phases. Some previous work combined them together, like run and dispute preparation, but for the sake of this talk, we'll separate them. So the first family of protocols are the optimistic circuits protocols. Here, during the commit phase, we take the program, we break it down into an arithmetic circuit. This arithmetic circuit represents the computation where each gate is one simple arithmetic operation. The main idea is that if there are loops in the original computation, we have to unroll them because the expressiveness is limited. We then take the entire circuit and Merkleize it. And then the root of this Merkle tree acts as a reference for any future dispute for the smart contract. The run phase is pretty simple. One of the parties just executes the computation, submits it on-chain. And then if the other party disputes the computation, we begin with the dispute preparation phase. Here we take the intermediate gates values or outputs and Merkleize them again and submit them. Each party submits them to the smart contract as a commitment to their computation. The dispute phase then initiated, and during the dispute phase, the parties run bisection protocol, which is essentially a distributed binary search. They identify the first gate that they disagree on, which means that whatever comes before this gate
is accepted by both parties. And specifically, the inputs to the dispute gate are also fixed. This means that the smart contract can execute the gate very simply by just taking the inputs and calculating the outputs. This is very efficient, and in the end of this process, the smart contract knows who is the cheater and outputs the correct result. The problem with this approach is that it's not Turing-complete. We can express only very limited programs with that. Also, we don't have random memory access that is required in many applications in ML. The second type of protocols are the optimistic VM protocols. Here, during the commit phase, we take the program and break it down into some low-level language, like MIPS, like WAVM. And then we Merkelize the commands of this low-level language and again commit to the smart contract using the Merkle root. The run phase is the same. One of the parties executes the computation, and the other party can dispute. And then during the dispute preparation, we take the intermediate VM states, meaning that we take the MIPS simulated machine that we run those low-level operations on, and Merkelize all the states between the commands. And then we initiate bisection for the intermediate states, identify the first state that we disagree on, and the smart contract can then execute the single low-level language command and calculate the correct state and identify the cheater, as before. This protocol is used by many layer 2 solutions, like Arbitrum, Optimism, etc. The problem with this approach, it is not very well parallelized, meaning that because of this state commitments, we can't run it in multi-threads. Another disadvantage is that in most implementations, we are required to have some log memory taxation for every write operation during the dispute preparation. And this is because we have to update the Merkle root on every memory write. And this is quite heavy for memory-intensive operations, such as matrix multiplication, that are very common in the ML world. So far, we saw two families of protocols. The first one is not expressive enough, and the second one has limited parallelism. And you might ask yourself, who cares? Why would we even care if disputes are very rare? And the intuition here that this might be an argument for layer 2 solutions where the end computation is not too heavy, but for ML workload, this might be critical, because if the computation is infeasible, it means that one of the parties, or malicious party, can submit incorrect result, and nobody would be able to challenge it. So the happy path is only relevant when the threat is real. The same goes with honest parties that submit correct result, but can be falsely accused, and during the dispute, they won't be able to participate because the computation is too heavy for them. So this is why efficiency means security in this case. So Arbigraph is our new protocol that uses a dual graph architecture. It takes the middle ground between the two approaches I described earlier. Here we have the symbolic graph that acts as a commitment for the initial commit phase. And we have the execution graph, which is the actual execution trace. And this is the part that we bisect on. So I'll give you an example of how those graphs are built. We have one very simple program here that initializes a variable and then writes into a dynamic memory location, and then does two loops. So the symbolic graph would be very simple. It is very similar to arithmetic circuits, only that we support also branches and tensor writes in this case, which is memory write. And we have the execution graph, which is the trace of the execution and is typically much larger than the symbolic graph. In this case, we unroll the loop and we take the actual branches that the program took. And as you can see, almost every command in the original program translates to one node in the symbolic graph. If we go back to the 4 phases, during the commit phase, we take the program, we break it down to a symbolic graph, we then commit on the symbolic graph using Merkle tree and Merkle root, as before. The run phase, one party executes the program, and then during the dispute preparation phase, we convert the symbolic graph into an execution graph. We then commit on the execution graph with the Merkle tree, and during dispute, we, as before, identify the first node of the graph that both parties disagree on, of the execution graph. Once we identify this node, the smart contract is able to execute the full node and identify the correct result. The difference from previous protocols that the proofs parties provide to the smart contract are much more complicated because we introduced a new complexity. Let me demonstrate with an example. Here we have some memory read in location 2, and Bob might provide an older version of the write to this same location as a part of the proof to the arbitrator. Now, by looking just at Bob's proof, the arbitrator can't really tell that Bob is lying because he doesn't have access to the full execution graph. But when Alice provides her write, which is more recent, the arbitrator can just check their location in the Merkle tree and identify that Bob is the malicious party and output the correct result, which is Alice's result. So this is just a small example. In reality, there are more nuanced cases, and this is why we create a full security proof. We have 4 properties that we prove: completeness, soundness, and progress. Completeness means that if both parties are honest, they would the output would be their result, and no party would be incriminated. Soundness means that if one party is malicious, the output will be, it would be identified, and the output would be the output of the honest party. Progress means that the entire protocol terminates within log n rounds, or O log n rounds. So now the last part of this talk, I'll talk about evaluation. We implemented Arbigraph fully on using Karpathy's Llama C implementation. We constructed multi-level execution and symbolic graphs. The entire dispute process was 37 rounds, exactly because of this multi-level architecture that requires bisection at every level. Totally, it required 56 transactions. The full dispute costed $6.5 million gas, which roughly equal to between $100 and $1,000 on layer 1, depending on the network load. The entire execution has few modes. We can optimize memory or optimize performance. So theoretically, we can even execute it on a laptop because the symbolic graph teaches us in advance which nodes should be evacuated, can be evacuated, and which nodes are needed for future reference. And so it runs between 59 gigabytes to 1.2 gigabytes of RAM, extra, of course, to the weight model. The entire dispute preparation for Qwen 2.57 billion parameters took 260 seconds for a single thread and 9.5 seconds for 64 threads, which is almost 30 times speed up. So parallelism works really great here. We also compared to Nitro Prover, production prover. Specifically, Nitro can't really handle large models such as 7 billion parameters models because of inherited limitation in memory. But we compared for large matrix multiplication, which is the basic building block of every ML computation. And we showed that when we compare replay versus replay, even for Arbigraph that runs on a single core, we have almost 8 times speed up for a matrix of 8,000 on 8,000 elements. And when it comes to multi-thread run, we are almost 60 times faster than Nitro. So to sum up, Arbigraph is a new protocol that is parallel by design. We don't require single-state mutation as in the case of optimistic VM. It is 01 in memory access. We don't have imposed this pair write tax that I showed you earlier. It is fully Turing-Complete. We support dynamic branching and random memory access. And we were able to execute a real 7 billion parameter model with 6.5 million gas consumption. Thank you very much. I'll be happy to answer questions.
Thanks, Michael. I think we have time for questions. So before anybody comes up, I had a question. Maybe I'll wear Dan's hat and ask you, like, you seem to use just hash functions, is it? So is it already post-quantum secure?
Sorry?
You seem to use only hash functions, or am I incorrect in assuming that?
Yeah, we have only hash functions, Merkle trees. That's our security assumptions, basically.
Okay, so already post-quantum secure.
Yeah.
Okay, great. Any questions? Okay, if not, then let's thank the speaker. That's all for the ZK session. Thank you for attending the talks. And let's thank all the speakers.